For years we believed, yes, it was our destiny to find a second Earth at the nearest star. When Proxima b was discovered in 2016, we thought the universe had given us a gift. But we were terribly wrong, because this was not a gift. It was a brutal lesson in physics. That so-called close distance is actually 40 trillion kilometers. This is why even with our fastest spacecraft, the journey would take 6,700 years. This means the passengers would die thousands of years before arrival. But that's not the truly terrifying part. The real question is, even if we solve the problem of speed, how would the human body endure a journey lasting decades? Because this is more than an engineering challenge. It's a war for survival. If you also think the harsh realities of space are exciting, then like this video and subscribe to the channel, because you're about to see how humanity's greatest dream turns into a nightmare. Here we go. You hear that our nearest star is only 4.24 light-years away. That word "only" is the most dangerous lie in astronomy. Because 4.24 light-years means 40 trillion kilometers. When humanity first heard this number, they thought it was a game of fate. They thought the universe had placed a second Earth at the shortest possible distance. They felt challenged. It was as if it was saying, "Come and get it." But that was before we understood the difference between naming a destination and being able to reach it. The distance between those two ideas is where the story turns from an inspiring dream to a much more unsettling reality. So, we must start from the very beginning, from the most basic concept, the discovery of the planet Proxima Centauri. Electrified the scientific world. The headlines wrote themselves. The nearest potentially habitable world is on our doorstep. That sentence sounds wonderful, because the words perform a psychological magic that hides the physical reality. The word nearest denotes a rank, not an accessibility. Being at the top of the list among the hundreds of billions of stars in the Milky Way does not mean it is close in any sense that human engineering currently recognizes. Imagine standing on the shore of the Pacific Ocean, and someone tells you that the nearest land across the water is 8,000 kilometers away. You can accurately call that point the nearest. But if you have no boat, no fuel, and no proven method of surviving the crossing, the word nearest begins to sound less like a comfort and more like a taunt. And that is exactly what Proxima Centauri is. So what does 4.24 light-years mean? This is a scale at which our intuition fails, because a light-year is the distance light travels in 1 year at a speed of 299,792 kilometers per second. In 1 second, light circles the Earth 7.5 times. In 1 minute, it crosses the orbit of Mars. In about 5.5 hours, it leaves Pluto's orbit behind. But then the scale changes. After passing the outermost objects in our solar system, light enters the interstellar void. And the next milestone is Proxima Centauri. Light that leaves our sun right now will arrive there in 4 years, 2 months, and roughly 17 days. 1 light year is about 9.46 trillion kilometers. So, when you multiply that number by 4.24, you get the distance to the nearest star, approximately 40 trillion kilometers. This is a void our minds cannot comprehend, and this void contains every distance humanity has ever crossed, thousands of times over. So, the real question we must now ask is this: how long would it take a human-made object to cross a distance that even light takes more than 4 years to travel? This is where the real nightmare begins. Consider the Voyager 1 spacecraft, launched in 1977. It is the most distant human-made object in existence. After nearly 50 years of continuous flight, it has traveled about 165 astronomical units from Earth. It is moving through interstellar space at about 17.3 kilometers per second. That's about 62,000 kilometers per hour. That sounds impressive. But it is nothing when measured against the distance to Proxima Centauri, because at Voyager 1's current speed, the journey would take about 73,000 years. 73,000 years. That is roughly 10 times longer than all of recorded civilization. When Voyager 1 hypothetically arrives at Proxima Centauri, the entire history of writing, agriculture, cities, empires, and science would fit into just the first 15% of its travel timeline. This is not an engineering problem, it is a time problem, but we have faster craft, right? Let's take the Parker Solar Probe, the fastest spacecraft ever built by humans. During its closest approaches to the Sun, Parker reaches speeds of about 191 kilometers per second. That's 690,000 kilometers per hour, fast enough to travel from New York to Los Angeles in about 20 seconds. So, a journey to Proxima Centauri at Parker's maximum speed would take about 6,700 years, 10 times faster than Voyager. But still longer than the time separating us from the construction of the Great Pyramid at Giza, still longer than the entire combined history of ancient Egypt, Greece, Rome, the Middle Ages, the Renaissance, the Industrial Revolution, and the Space Age. And yet, here is the crucial point. The Parker Solar Probe only reaches this speed for brief moments when it is closest to the Sun. No spacecraft can sustain anything close to this speed in open interstellar space. Because no propulsion system currently in operation can maintain such velocities over the required distances. These are not abstract numbers. They are the engineering realities that define the boundary between what humanity has accomplished and what the nearest star demands. We have sent probes past every planet in our solar system. We have landed machines on Mars, Titan, and a comet. But every one of these achievements took place within a radius of about 50 astronomical units from Earth. The nearest star sits 268,000 astronomical units away. The gap between our farthest success and our nearest stellar target is not a gap. It is an abyss so vast that every unit of distance humanity has ever crossed fits into it thousands of times. So, the problem is not whether we have a target. The problem is whether any propulsion system humanity can realistically build can bridge that gap. Because, right now, even the fastest spacecraft in history needs thousands of years to make the crossing, and the technologies that could reduce that timeline to decades have never left a laboratory, a whiteboard, or a computer screen. So here is what we understand. The nearest star is unimaginably far away. Our fastest ships are as slow as a snail. This is why engineers had to abandon conventional rocketry entirely. They turned their eyes to something far more exotic, far more powerful, to the heart of the atom, to nuclear pulse propulsion, fusion engines, even antimatter. Because the only way to close this distance was to escape the tyranny of the rocket equation, all one but. These new technologies brought their own nightmares, and the first of these nightmares was the most violent propulsion system humanity has ever designed. And this system was one of the most audacious and terrifying ideas ever conceived to reach Proxima Centauri. It was called Project Orion, designed in 1958 by physicists Ted Taylor and Freeman Dyson. The concept was mechanically simple, but physically terrifying, because it proposed detonating nuclear bombs behind a giant pusher plate attached to the back of the spacecraft. Each explosion would slap the plate forward, accelerating the ship incrementally. The idea was, literally, to ride a starship on the blast of atomic bombs. So, Orion was a product of the Cold War's unshakable faith in nuclear power. Dyson's calculations showed that an Orion vehicle using pure deuterium fusion explosions could achieve an exhaust velocity of about 15,000 kilometers per second. This was equivalent to about 6.7% of the speed of light, and it would reduce the flight time to Alpha Centauri to roughly 130 years. But the scale of this beast was mind-boggling. The interstellar Orion ship would have a mass of about 100,000 tons, and it would require millions of nuclear pulse units. The ship itself was the size of a city. So, the engineering challenges were staggering, even by the standards of a civilization accustomed to nuclear arsenals. But what ultimately ended Orion as a practical program was the 1963 Partial Nuclear Test Ban Treaty. This treaty banned nuclear explosions in space, and it became Orion's tombstone. Because these ideas were just the beginning. Project Daedalus arrived. It was a study conducted by the British Interplanetary Society between 1973 and 1978. Daedalus refined the nuclear pulse concept by using inertial confinement fusion instead of fission bombs. It proposed firing high-powered electron beams at small pellets of deuterium and helium-3. It would create 250 controlled fusion explosions per second. The design called for a two-stage spacecraft weighing about 54,000 tons at liftoff. The first stage carried 46,000 tons of fusion fuel, and the second stage carried 4,000 tons. Daedalus was designed as an unmanned flyby probe targeting Barnard's star, about 6 light-years away, and the estimated flight time was 50 years. The cruising speed was 12% of the speed of light. But 2 details about Daedalus illuminate the scale of the problem, and this is crucial. First, the design required helium-3 as fuel. This substance is so rare on Earth that the entire global supply would not fill a small room. The Daedalus designers proposed mining helium-3 from Jupiter's atmosphere using giant balloon platforms. This alone would be a civilization-scale enterprise, and it would require technologies we do not possess. Second, even this extraordinary machine, burning 50,000 tons of exotic fusion fuel, could only perform a flyby. It had no capacity to slow down at its target, enter orbit, or make long-term observations. It was a bullet fired at the stars. It was fast, it was expensive, and it could not stop. This problem of deceleration is one of the most underappreciated hurdles in interstellar mission design. Because getting there is only half the problem, this is why one of the latest and most popular ideas tried to change this equation entirely. Breakthrough Starshot. This project proposed accelerating the spacecraft with a ground-based laser array. Instead of carrying fuel on board, a laser array generating about 100 gigawatts of directed power would focus a beam on a reflective light sail roughly 4 meters wide, attached to a gram-scale payload called a starship. The photon pressure from the beam would accelerate the sail to 20% of the speed of light in about 10 minutes. This would subject the tiny payload to accelerations of tens of thousands of times Earth's gravity. At 20% of the speed of light, the vehicle would reach Proxima Centauri in about 21 years. But the same problem remained. Upon arrival, it would fly past the system at 60,000 kilometers per second. It would collect data during an encounter lasting only a few hours, and then it would continue into interstellar space. It would never stop. Breakthrough. Starshot reduced the problem to its most minimal form. By leaving the energy source on the ground, it eliminated the need to carry fuel. By shrinking the payload, it reduced the energy required to reach relativistic speeds, and by giving up any pretense of slowing down, it avoided the fuel penalty of braking. But even this minimal version proved to be extraordinarily difficult. The laser array had to produce 100 gigawatts of coherent power, roughly equivalent to the output of 100 large nuclear power plants. The sail material had to withstand the beam without vaporizing. And the Starship itself had to carry a camera, a power source, and a laser communication device capable of sending data from 4.24 light-years away, all within a mass budget of a few grams. The result? The project stalled. After spending about $4.5 million of the initially committed $100 million, it was put on indefinite hold, because it collided with engineering reality, and Breakthrough Starshot was never a human mission concept. It was the smallest, lightest, fastest possible version of reaching another star. There was no life support, no radiation shielding, no food, water, air, or crew quarters, just a chip and a camera, a bullet that could not be stopped. This was the version that failed. Now let's put all these concepts together: the speed problem, the deceleration problem, and the fuel problem. These are all different faces of the physical reality of interstellar distance. Each one, on its own, dwarfs any engineering challenge humanity has ever faced. But now we wonder, what if we solved all these propulsion problems? What if, a century from now, we have a fusion engine? What if we could get to Proxima Centauri in 40 years? Would that mean victory? But the truly unsettling reality is that speed was never the only problem. Speed was just the most visible one. But even if speed is solved, another category of challenges remains, a problem that cannot be addressed with faster engines or more powerful lasers, because this problem lies not in the distance between stars, but in the fragility of human bodies, the limits of human psychology, and the finite reliability of every machine ever built. This is a problem that may be even harder than the propulsion problem, because a 1-gram probe doesn't eat, it doesn't breathe, and it doesn't get cancer. but yeah, people are entirely different from a 1-gram probe. A probe doesn't eat, it doesn't breathe, it doesn't get cancer from cosmic ray exposure, it doesn't experience loneliness, anxiety, lust, or depression. This is where the real shock begins, because no matter how immense the propulsion problem is, it is only a problem of engineering and energy. But the problem that comes now is different. It is biology, endurance, and the brutal reality that keeping people alive for decades between the stars may be harder than getting them there in the first place. Let's face the first shock, radiation. It is a killer. You can't see it, you can't touch it. But it is there. Interstellar space is saturated with galactic cosmic rays, high-energy particles originating from supernova explosions across the Milky Way. When these particles hit biological tissue, they shred DNA, they break molecular bonds, and they create cascades of secondary particles that spread the damage to surrounding cells. The numbers are terrifying. On Earth's surface, you receive about 2.4 millisieverts of radiation per year. On the International Space Station, that number rises to as much as 320 millisieverts per year. But in interstellar space, that number skyrockets to 600 millisieverts per year. On a 40-year journey at 10% of the speed of light, a crew member would be exposed to a total dose of about 16 to 24 sieverts. Let's understand what that number means. A dose of 5 sieverts received at once is fatal for 50% of people. 20 sieverts is absolutely lethal. The career limit for a NASA astronaut is just 600 millisieverts. This journey exceeds that limit 40 times over. This should not have happened. We should have had a shield against this. But here's the most terrifying part. Conventional shielding makes the problem worse, because when high-energy particles hit dense materials like lead, they create showers of secondary particles that are even more dangerous. The shield can kill you faster. So let's assume you somehow survive the radiation. You still need to breathe, you need to drink water, and you need to eat. Here comes the second shock, the life support trap. Consider the International Space Station, the most advanced closed-loop life support system ever built. It recycles about 98% of its water. But even that is not enough. That 2% shortfall must be made up by resupply missions from Earth. Oxygen is supplemented by deliveries from cargo vehicles. Food comes entirely from Earth, and the station's critical systems have failed repeatedly. Each time, the repair depended on spare parts from Earth or real-time help from engineers on the ground. But a Starship has none of that. No resupply missions, no spare parts, and a years-long delay in communication with Earth. This means the life support systems must operate in a 100% closed loop for decades, with zero loss. Such a system has never been built. The closest attempt was the Biosphere 2 experiment in Arizona, and it ended in complete failure. Oxygen levels dropped dangerously, carbon dioxide fluctuated, and the crew starved. This was done on the surface of the Earth, with unlimited solar energy and the ability to abort at any moment. A Starship has none of these luxuries. The ship doesn't explode, it slowly becomes uninhabitable. But imagine you do everything perfectly. Your radiation shield works, your life support is flawless. What about the ship itself? Here is the third and perhaps most insidious shock, the mechanical reliability nightmare. The longest-running, continuously operating human-made systems in space are the Voyager probes. They have been operating for almost 50 years. But they're extraordinarily simple by the standards of a crewed ship. Voyager's primary structure has no moving parts, it carries no life support, and its instruments are slowly dying. By the mid-2030s, Voyager will no longer have enough power to operate any of its instruments. But a crewed Starship is not a passive probe. It is a city in a bottle. It has pumps, valves, compressors, computer networks, water purification systems, and food production equipment. And every one of these systems contains components that wear out, corrode, or break over time. Nothing lasts forever. But an interstellar mission demands that everything last for a very long time. On Earth, you replace a broken part, but between the stars, Every spare part must be carried on board or fabricated in transit. Carrying spares for every possible failure would increase the ship's mass to impossible levels. Fabricating parts with 3D printers? Current technology cannot print a precision bearing or a high-pressure valve seal. So, the failure of a single critical system ends the mission. Because there are no spare parts, repair is not possible, and there is no such thing as rescue. Radiation kills you, lack of air kills you, and a broken machine kills you. These are all the brutal limits of the human body and human engineering. They are as real as the laws of physics, and none of these problems have a proven solution, only speculative concepts, and each concept brings its own impossibilities. But even if we overcame all these physical, biological, and mechanical obstacles, the biggest unknown would still remain. It is the most unpredictable variable in the equation, the human mind. Because in a 40-year journey, inside a sealed metal can, the piece that breaks most easily is not the one made of steel or titanium. But that piece is the human mind. This is the fourth shock, psychological collapse. Studies on extreme isolation and confinement consistently document significant psychological effects. We've studied crews in Antarctic research stations, we've analysed submarine missions, we even conducted the Mars 500 experiment. In this experiment, 6 volunteers were locked in a sealed facility for 520 days. The results were disturbing. Depression, anxiety, interpersonal conflict, sleep disturbances, cognitive decline, and loss of motivation. Several crew members in Mars 500 became increasingly inactive. Their sleep-wake cycles became disrupted, and they showed measurable declines in their alertness and cognitive performance throughout the simulation. And that was just 520 days, less than 2 years. With the knowledge that the experiment would end, a normal life would resume. An interstellar mission offers no such assurance. The crew leaves knowing they will not return to Earth for decades, perhaps never. Communication with friends and family becomes increasingly abstract as the light speed delay stretches from minutes to hours and then to years. After a few years of flight, the crew exists in a communicative void. Messages from Earth arrive years after they are sent, describing events and people that have changed beyond recognition in the interim. This should not have happened. The human mind is not designed for this kind of disconnection. So, as the human spirit struggles to survive, a fifth shock knocks on the door, the governance nightmare. Was because when you put a group of people in a sealed box for decades, eventually the basic rules of society break down. Every human community requires systems of authority, decision-making, and conflict resolution. But on a starship no one can leave. The community is sealed, it is permanent, and it is inescapable. Who will govern the ship? A military-style hierarchy offers clarity of authority. But it risks devolving into authoritarianism in the long run, because there are no oversight mechanisms from Earth. A democratic model, on the other hand, could lead to factional disputes, gridlock, or the tyranny of the majority, because us minorities have nowhere else to go. But the most terrifying question is this: leadership succession. A mission lasting 40 to 100 years will outlive the functional career of any individual leader. What happens when the original commander dies or retires? The transfer of authority in a sealed, isolated community is historically one of the most destabilizing events any society can face. A mutiny doesn't just destabilize the society, it threatens the physical survival of every person on board. Because the ship's operation depends on coordinated technical management, which a failure of governance can disrupt. And then there are the children. Those born on the ship. They did not choose this mission. But it is their prison. This is a moral black hole. Because, while all these social and psychological dramas play out, a crew member's appendix bursts, or someone has a heart attack, and you meet the 6th shock: medical impossibility. Medicine on a starship presents problems with no parallel in current spaceflight experience. If the mission carries a doctor, that doctor must be prepared to handle every medical scenario that could arise in a population of hundreds over decades. Acute surgical emergencies, heart conditions, strokes, dental infections, and cancer. Surgery in space is primitive. Performing open surgery in microgravity presents practical challenges. Blood does not pool in a wound. It forms floating globules that obscure the surgical field and contaminate the cabin atmosphere. Bodily fluids drift freely. And all this happens in an environment where, even with artificial gravity in a rotating habitat, Coriolis effects can cause nausea and disorientation that complicate delicate manual procedures. Yet no human surgical procedure has ever been performed in space. The ship's drug supply is finite, and antibiotic-resistant bacteria, which can flourish in a closed environment, can render those drugs useless. Studies on the International Space Station have shown that microgravity can increase the virulence of certain types of bacteria, while simultaneously suppressing some aspects of human immune function. This is a perfect storm, and most importantly, there is no possibility of evacuation. A condition that would be treatable on Earth becomes a death sentence on a starship, because the nearest hospital is 40 trillion kilometers away. Radiation, suffocation, machine failure, psychological collapse, social disintegration, medical catastrophe. Each of these is a massive wall blocking the path to Proxima Centauri, and each one, on its own, is enough to make the mission impossible. Even if we forget the propulsion problem for a moment, the problem of keeping a human alive seems to be an insurmountable obstacle. But let's put all these problems aside. Let's go back to the beginning, to those engines, to those shields, to those systems, those complex machines designed to prevent all these nightmare scenarios. How do they actually work? And more importantly, why does each one contain a separate impossibility within itself? Because when we get down to the heart of the propulsion system, we face the gap between the promises of physics and the brutal reality of engineering. But that piece is the human mind. And in a 40-year journey, inside a sealed metal can, the piece that breaks most easily is not the one made of steel or titanium, but the human spirit. But let's put all these problems aside. Let's go back to the beginning, to those engines, to those shields, and to those systems. Those complex machines designed to prevent all these nightmare scenarios. How do they actually work? Because when we get down to the heart of the propulsion problem, the radiation shield, or the life support system, we face the massive chasm between the promises of physics and the brutal reality of engineering. Now let's slow down and get technical. Let's understand why each system contains both a promise and an impossibility. First, let's go down to the principle that started it all. As every propulsion system humanity has used to explore space relies on the same basic principle. You throw mass out the back of your vehicle as fast as you can, and Newton's third law pushes you forward. This is like standing in a boat and continuously throwing stones backward. Each stone pushes you forward a small amount. Chemical rockets throw out superheated exhaust gases. Ion engines throw out electrically accelerated atoms. But the basic idea is the same. The differences between these systems boil down to two variables: how fast they can throw that mass, exhaust velocity, and how much energy they can extract per kilogram of their fuel. These two numbers define the limit of what any propulsion system can achieve. And for interstellar travel, every system we have ever built falls catastrophically short. Chemical rockets, the workhorses that carried humans to the moon and sent probes across the solar system, produce exhaust velocities of about 3 to 4.5 kilometers per second. This is impressive for escaping Earth's gravity. But it is useless for reaching another star. Because as chemical rockets are caught in a brutal mathematical trap known as the rocket equation. This equation states that the speed a rocket can reach increases exponentially with its fuel mass. The energy density of chemical fuels, about 10 million joules per kilogram for liquid hydrogen and liquid oxygen, is simply too low. A chemical rocket trying to reach Proxima Centauri would have to carry so much fuel that the fuel itself would require a fuel tank larger than planets. So, chemical rockets are not even a starting point for interstellar travel. They are the proof of why this journey requires a different way of thinking. This is why engineers looked for ways to increase efficiency, and they found electric propulsion systems. Concepts like ion engines and Vasima represent a real advance over chemical rockets in one regard. These engines achieve much higher exhaust velocities, typically 20 to 50 kilometers per second for ion thrusters, potentially hundreds of kilometers per second for advanced plasma engines. A higher exhaust velocity means fuel is used more efficiently. It's like throwing a bullet instead of a baseball with the same effort. The bullet goes much faster. This makes electric propulsion perfect for missions within the solar system. But while there is a trade-off, and it is a fatal one: thrust. Electric propulsion systems produce an extraordinarily low thrust relative to the spacecraft's mass. A typical ion engine produces a force measured in fractions of a newton, similar to the weight of a sheet of paper resting on your palm. These engines accelerate the spacecraft slowly. They gain speed by firing continuously for months and years. For interstellar travel, this creates a devastating timeline problem. Reaching even 1% of the speed of light, roughly 3,000 kilometers per second, would require decades of continuous thrust, and reaching 10% of the speed of light would require thrust times of centuries, and power levels far beyond what an onboard reactor could provide. Electric propulsion trades thrust for efficiency, and that trade-off makes it great for navigating the solar system, but useless for crossing the abyss between stars. The engines that work best in our neighborhood are exactly the wrong tools for the journey beyond. So, the inadequacy of chemical and electric propulsion forced humanity to break the nucleus of the atom. And this brings us to Project Orion. This was the first serious nuclear concept for interstellar propulsion. And it was an act of pure brutality. Designed in 1958, Orion proposed detonating nuclear bombs behind a giant pusher plate attached to the spacecraft. Each explosion would slam a cloud of plasma and debris into the plate, kicking the ship forward. It was like trying to accelerate a car by continuously detonating hand grenades behind it. But it was physically sound, because reactor nuclear fission releases about 80 trillion joules per kilogram of fuel. That is about 8 million times more energy per kilogram than the best chemical fuels. Dyson's calculations showed that an Orion vehicle could reach an exhaust velocity of about 15,000 kilometers per second and 6.7% of the speed of light. This would reduce the journey time to Alpha Centauri to about 130 years. This was the first concept that made it mathematically possible to reach the stars within a few human lifetimes. But the cost was terrifying. The ship's mass would be about 100,000 tons, and it would require millions of nuclear pulse units. This was an engineering nightmare, but what killed Orion was not its engineering, but its morality. Psychior. The 1963 Partial Nuclear Test Ban Treaty banned nuclear explosions in space, effectively consigning Orion to the dustbin of history. The physics remains valid, but civilization would not allow it, because the ideas that came after Orion tried to control the nuclear fire more elegantly. Project Daedalus used the concept of inertial confinement fusion. This meant creating hundreds of miniature fusion explosions per second by firing electron beams at small fuel pellets instead of a giant atomic bomb. This was to provide thrust with continuous explosions like a machine gun. Daedalus was designed to reach 12% of the speed of light, and it predicted a 50-year flight time to Barnard's star about 6 light-years away. But it had 2 fatal flaws. First, its fuel was helium-3. This was an isotope that is virtually non-existent on Earth. The designers of Daedalus proposed mining it from the atmosphere of Jupiter. This, in itself, was a civilization-scale project requiring technologies we don't have. Second, and more importantly, Daedalus had no ability to decelerate. It would enter its destination at 36,000 kilometers per second and fly past. This reveals one of the most brutal realities of interstellar mission design, the deceleration problem. When you arrive at your destination, slowing down requires as much or even more energy than accelerating. Because, for a rocket-powered spacecraft, this roughly doubles the fuel requirement. Fuel to accelerate, fuel to decelerate, and fuel to carry the fuel you will need later. The exponential math of the rocket equation becomes brutal here. Concepts like Daedalus and Orion showed us one thing very clearly. Reaching the stars is not just about finding more energy. It is about how we control that energy, how we direct it, and most importantly, how we stop at the end of the journey. And that control required more than the brute force of fission. This was humanity's attempt to trap the sun in a box and turn it into an engine. And this quest led us to fusion propulsion. Fusion is the same process that powers the stars, and in theory, it is the most promising technology for practical interstellar travel. Fusion reactions release roughly 3 to 4 times more energy per kilogram than fission, and they produce far less radioactive waste, It's like comparing a wood stove to a nuclear reactor. The leap in energy density is that great. A fusion-powered spacecraft could theoretically achieve exhaust velocities of 10,000 to 30,000 kilometers per second. At the upper end, this reduces travel times to Proxima Centauri to a few decades for a flyby, and perhaps less than a century for a mission that includes deceleration. This, for the first time, opens the door to a round-trip mission that could be completed within a human lifetime. But the word theoretical here is critical, because controlled fusion remains one of the most difficult, unsolved engineering challenges on Earth. As of 2026, no fusion reactor in the world has produced sustained net energy output. The ITER experimental reactor in France is the largest fusion project ever attempted, but it has faced repeated delays and cost overruns, and its deuterium-tritium fusion experiments are not expected to begin before 2039. ITER is a stationary facility the size of a large building. It is supported by the combined resources of 35 countries, and turning that massive ground installation into a compact, lightweight, space-rated engine that can operate reliably for decades without maintenance represents such a massive engineering leap that there is no credible timeline for its completion. We are not developing fusion propulsion. We have not yet invented fusion propulsion. So, the fusion engine itself remains a product of imagination. What about the problem of turning it into an engine in space? That is an even bigger nightmare. Because the most advanced fusion project on Earth, ITER, is a tokamak reactor. It uses superconducting magnets cooled to near absolute zero to confine a plasma with a temperature exceeding 150 million degrees Celsius. The tokamak machine alone will weigh about 23,000 tons, and it requires external power measured in hundreds of megawatts to operate. A fusion rocket, on the other hand, requires something completely different. It must convert fusion energy into directed exhaust momentum. It must expel the reaction products out of a nozzle at extremely high velocities. This is a problem of plasma physics, magnetic confinement geometry, materials engineering, and thermal management, and it is completely different from the problem of sustaining a fusion reaction in a stationary laboratory. A space-rated fusion engine must be compact, it must be lightweight, and it must be robust enough to operate continuously for years. It must manage the neutron flux from the fusion reactions, because this flux degrades structural materials over time, and this must be done in the vacuum of space, where waste heat can only be shed by radiation. This requires massive thermal radiator surfaces, and this also adds mass and complexity. So, the gap between a ground-based fusion reactor and a flight-ready fusion engine is not a gap of improvement. It is a gap of reinvention, and it is a gap humanity has not yet crossed. But what if we eliminated the fuel equation entirely? This was the radical idea behind the Breakthrough Starshot project. Instead of carrying fuel on board, push the spacecraft with a powerful laser beam sent from the ground. It's like the wind pushing a sailboat. Yeah, but instead of wind, you use light. Photons. The concept relies on photon pressure. Light itself exerts a tiny amount of push on a surface it hits. This push is incredibly small for a single photon. But a sufficiently intense laser beam can impart significant acceleration to a lightweight sail. Starshot designed a phased array laser array generating about 100 gigawatts of power. This is roughly equivalent to the total output of 100 large nuclear power plants. This massive power would be focused on a 4-meter light sail. The sail would be attached to a gram-scale Starship payload. The photon pressure from the laser would accelerate this tiny craft to 20% of the speed of light, 60,000 kilometers per second, in just 10 minutes. This completely bypasses the rocket equation. Because the propellant, photons, is not on the ship, it stays on Earth. This in theory removes the biggest obstacle to interstellar travel, but in practice it creates its own set of impossibilities. The laser array itself would be an unprecedented engineering marvel. Millions of individual laser elements would have to work in perfect synchronization. The sail material would have to withstand this intense beam without vaporizing, and the Starship itself would have to house a camera, power source, navigation system, and a communication device within a mass of a few grams. Starshot could not solve any of these problems. The project stalled after spending only 5% of its budget. Because No matter how elegant the idea, the engineering reality was that brutal. So, chemical rockets are too slow. Electric propulsion is too weak. Nuclear fission is too dangerous. Fusion has not been invented yet, and laser sails are too difficult. Where does this leave us? At the most extreme theoretical end of the spectrum, antimatter propulsion. When matter meets antimatter, they both annihilate completely. They convert 100% of their combined mass into energy. This is the highest energy density physically possible. It is roughly 300 times greater per unit mass than fusion. In theory, a spacecraft carrying just a few hundred grams of antimatter could generate enough energy to reach a significant fraction of the speed of light. This seems like the holy grail of interstellar travel. But, in practice, the challenges are almost absurdly severe. First, production. The total amount of antimatter humanity has produced in all its particle accelerators throughout history is about 20 nanograms. Measured in nanograms, not grams, that is billionths of a gram. Second, storage. Antimatter must be stored without touching normal matter. Because any contact causes instant annihilation. And third, use. When matter and antimatter annihilate, much of the released energy comes in the form of gamma rays and neutrinos. Neutrinos do not interact with matter and are lost. Gamma rays are extremely penetrating and require massive shields to protect the crew and equipment. Estimates suggest that only about 40% of the total annihilation energy can be practically captured and directed as thrust. Antimatter is the best solution on paper. But for in engineering, it is the most impossible one. When we lay all these technologies on the table, a disturbing picture emerges. Each propulsion system solves one problem while creating another. Chemical rockets are reliable but weak. Electric propulsion is efficient but slow. Nuclear power is energetic but dangerous and difficult to control. Laser sails solve the fuel problem but require massive infrastructure. Each has its own insurmountable obstacles. This means there is no single right answer. Perhaps the solution lies not in a single engine, but in a combination of these ideas. But what is truly exciting is that beyond all this theoretical discussion, each of these problems has led to incredibly audacious solutions that push the limits of human creativity. Because, in the face of these enormous challenges, engineers and scientists did not give up. They dreamed. And now, we will look at the most audacious of these dreams, the complete plan for the monumental mission that combines all these obstacles in a single endeavor and promises to take us to Proxima Centauri. But, when we get into the details of this plan, what we will realize is that this journey is not just an engineering test, but also a test of civilization. And the first question of this test is, and this quest was humanity's attempt to trap the sun in a box and turn it into an engine. But, beyond all these theoretical discussions, each of these problems has led to incredibly audacious solutions that push the limits of human creativity. Engineers and scientists did not give up. They dreamed, and now the real miracle comes. Now, we will look at the most audacious of these dreams. Here, the complete plan for the monumental mission that combines all these obstacles in a single endeavor. But, when we get into the details of this plan, what we will realize is that this journey is not just an engineering test, it is a test of civilization. Speed up, hold your breath. Because, now, we are diving into the heart of the largest, most audacious, and most impossible project in human history. A manned mission to Proxima Centauri. The whole thing, from start to finish. And it all begins in orbit. The first epic moment. Assembly. This is not a spaceship. This is a city built in orbit. A world we built not as a nation, but as a species. This ship must be large enough to house a crew of tens to hundreds of people. But that's just the beginning. Closed-loop life support systems, food production facilities, medical bays, repair workshops, raw material depots, and the radiation shield. All this adds up to a mass of tens of thousands, or even hundreds of thousands of tons. Consider a 100,000-ton ship designed for Project Orion. That is hundreds of times larger than the 450-ton International Space Station. Lifting such a structure from Earth's surface in one piece is impossible. So, it must be assembled in orbit, piece by piece. a massive construction project that will take decades. It will require thousands of rocket launches, each one carrying a small piece of the puzzle. This requires a multi-generational international effort, far beyond the resources ever committed to a single space project. How could this be possible? This is not a project, it is an era. It is a new industrial revolution for humanity, focused on a single goal. Yeah, and all of it must happen before the ship moves a single inch. What the scientific world sees when it looks at these numbers is not a budget problem. It is the ultimate test of political will and institutional endurance. It is a commitment that may last longer than the journey itself. Before the journey even begins, this is the largest structure humanity has ever designed, and it is only a beginning. Because, when that city is complete, the second epic moment arrives. Ignition, acceleration, the most powerful, longest and most energy-intensive engine burn in human history. The goal, 10% of the speed of light, 30,000 kilometers per second. The kinetic energy that must be transferred to that 100,000-ton ship to reach this speed pushes the limits of reason. That number is approximately 4.5 times 10 to the 25 joules. Let's put that number in context. The total annual energy consumption of all human civilization is roughly 5.8 times 10 to the 20 joules. The energy required just to get this ship to cruising speed is equivalent to 77,000 full years of our current global energy production. This is not a record. This is a verdict from physics on human ambition. This energy has to come from somewhere. Even a fusion engine operating at theoretical peak efficiency would require a fuel mass many times that of the ship itself. The rocket equation becomes a monster here. Every kilogram of fuel added increases the total mass that needs to be accelerated, which requires more fuel. It's a spiral. When scientists look at this equation, they don't see a problem of designing an engine. They see the problem of harnessing the power of a star to move a city. How could this be possible? This is not just about building an engine. It is about building a planetary-scale energy infrastructure, just to push that one ship. This is the greatest show of force in human history, and it is only the first step of the journey. Because, when the engines fall silent, the real nightmare begins, and here is the third epic moment. The cruise. 40 years of silence. The engines are off. The ship is now a bullet. But there are living people inside this bullet, and ahead of them lies a void of 40 trillion kilometers. This journey will take about 40 years. During this time, everything we have discussed before must work. But now the numbers are even more terrifying. Life support must operate for 40 years, about 14,600 days, without a net loss of a single drop of water or a single molecule of oxygen. And this is not something that has been tried for the first time in history. This is what is impossible to try. Food production must yield enough calories every year without a single major crop failure. Because the nearest grocery store is 4.24 light years away, and then there's the radiation. Over 40 years, each crew member will receive a cumulative cosmic ray dose that exceeds NASA's entire career safety limits 40 times over. That's 16 to 24 sieverts. This is a dose that no known biological repair mechanism can handle. Every pump, every seal, every circuit, every bearing, and every structural element on this ship must last far longer than its nominal lifetime, or it must be replaced using onboard manufacturing capabilities that do not currently exist. No machine runs forever. But this mission demands that everything run for almost forever. How could this be possible? This is not a journey. It is a 40-year war against entropy. It is the struggle for survival of a closed ecosystem in the most hostile environment known. This is not an engineering miracle. It demands a series of miracles that must continue uninterrupted for 40 years. When the scientific world looks at this, they don't see a reliability problem. They see a gamble against statistical certainty, and they know that over 40 years, the dice do not always roll in your favor. 0.24 light years, the cumulative bombardment from these particles is significant. The ship must withstand this continuous sandstorm. How could this be possible? Shielding concepts include sacrificial bumper shields that melt on impact, or the electromagnetic deflection of charged particles. But none have been tested under realistic interstellar conditions. During deceleration, the ship must reorient to fire its engines or deploy its braking systems. This potentially exposes different surfaces to the particle stream, or changes the geometry of its protective systems. This is the first time in history that a spacecraft will try to pass through a sandstorm at tens of thousands of kilometers per second. When the scientific world looks at this problem, they don't see a materials science problem. They see a game of roulette, a game played with billions of tiny bullets, and they know that just one of these bullets, hitting a critical point, can end a 40-year journey in a millisecond. This is the most expensive and fastest gamble in human history, and it is played every second, because even if you win this gamble, you face the seventh epic moment, reignition, the moment. After 40 years of silence, the engines must come back to life. But this is not just any engine. This is a fusion reactor that produces power equivalent to a civilization's energy output, and it has been dormant for 40 years, 14,600 days, in the brutal conditions of interstellar space, exposed to sub-zero temperatures, continuous radiation bombardment, and absolute vacuum. And now, it must work perfectly. This is a record. This is the first restart demanded of a rocket engine after the longest period of dormancy in history. Turbopumps, injectors, combustion chambers, fuel delivery systems. These are delicate components that degrade over time. Seals crack, bearings wear. Solder joints develop microfractures from thermal cycling. How could this be possible? This is not an engineering expectation. This is an act of faith. Scientists and engineers must believe that the machines they tested on Earth, under controlled conditions, will work decades later, in an environment that no one can simulate. A partial failure of the deceleration system means mission failure. A total failure means the crew is condemned to an endless death. This is the highest stakes technical test in human history. The line between success and disaster depends on whether a single valve, a single seal, or a single electrical circuit can withstand 40 years of wear and tear. And the result of this test will only reach Earth years later, but the engines worked. The ship slowed down, and the crew is experiencing the eighth epic moment, arrival shock. They are looking at the planet Proxima Centauri b, and what they see will determine the fate of the entire mission. But what do we see? What do scientists see with telescopes? Proxima Centauri is an active flare star. This means it regularly experiences explosions thousands of times more powerful than the Sun's. A superflare observed in 2019 increased the star's brightness by 14,000 times in just 7 seconds. This is the most powerful flare ever observed from a red dwarf star in history. This flare would have sent a massive amount of high-energy radiation and particles into the planet's atmosphere, if it has one. How could this be possible? How could life exist in such an environment? The planet would need a magnetic field hundreds of times stronger than Earth's to withstand this assault, or an atmosphere as thick as Venus's to begin with. But both seem unlikely, given the planet's mass and orbit. When the scientific world looks at this data, they don't see a habitable world. They see a radiation-sterilized caserne vol, scorched rock. This is the most brutal irony of the mission. While humanity tries to reach another world to survive, the first target it chooses may be one of the most hostile environments in the universe. At the end of a 40-year journey, the crew may find not a paradise, but a hell, and this is the outcome of humanity's greatest gamble. Because all these engineering and physics problems ultimately boil down to a single question. This is the ninth and final epic moment. Why? Why are we going? The answer lies in one of humanity's most fundamental instincts, the desire to explore. But also in a darker impulse, the desire to escape. As a species, we know that we have put all our eggs in one basket, planet Earth. An asteroid impact, a supervolcano eruption, or our own self-destruction. All of these could end our species. So, going to the stars is like an insurance policy. It is humanity's attempt to establish a foothold on another world. But what is the cost of this insurance policy? A ship of hundreds of thousands of tons, the energy output of a civilization, a commitment lasting generations, and the probability of failure is almost a certainty. How can this be rational? This is a civilization risking all its resources for a 0.001% chance of survival. This is not a decision that can be explained by logic. this is a decision that can be explained by hope, or perhaps desperation. When the scientific world looks at this why question, they don't see a strategy. They see a species confronting its existential fear, and they know that fear is not a good advisor. But sometimes, it is the only driving force behind the greatest achievements: assembly, acceleration, cruise, deceleration, and an unknown fate. Each of these is a monument to humanity's capabilities and limits. They remind us how big the universe is and how small we are. They show us how limitless our ambition is and how limited our tools are. These epic moments are not a story of victory. This is a story of a struggle with scale, with physics, and with our own fragility. And now, it is time to stand in the midst of this struggle and look beyond all these technical details, these records, and these impossibilities. Now, it is time to ask what all this journey means for us. Because, no matter how great the technical difficulties of building a starship are, the philosophical implications of this effort are much deeper, and these implications confront us with the most fundamental questions that define us as a species. Who are we? Where are we going? And in this vast cosmic ocean, are we truly alone? Because the greatest lesson the nearest star teaches us is perhaps not about engines or shields. Perhaps this lesson. And the reason behind the desire to reach Proxima Centauri is deeper than a simple urge to explore. It is a species confronting its existential fear. But now, it is time to put aside the noise of all these engineering challenges, these epic moments, and these unimaginable numbers, and slow down. It is time to stop and think, because no matter how great the technical difficulties of building a starship are, the philosophical implications of this effort are much deeper and much more personal. And now, we face the most important question. In this entire vast cosmic ocean, what is our place? This question confronts us with the most fundamental paradoxes that define us as a species. Because the greatest lesson the nearest star teaches us is perhaps not about engines or shields. Perhaps this lesson is about ourselves. And the first sentence of this lesson is a paradox of scale. On one hand, there is an all-encompassing, unimaginable vastness. We know the observable universe is about 93 billion light-years wide. We calculate that the nearest galaxy, Andromeda, is 2.5 million light-years away, the SIS, and we measure that even the nearest star, Proxima Centauri, is 40 trillion kilometers away from us. On the other hand, there is you, there is us, extremely fragile biological machines, about 1.7 meters tall, confined to an 80-year lifespan. How could this be possible? How can these microscopic beings in this insignificant corner of the universe take the measure of the universe itself? The tragic truth of this question is our physical insignificance. On a cosmic scale, we are nothing, less than a speck of dust. If the universe were an ocean, the Milky Way a continent, and our solar system a city, all of humanity would not even be a single grain of sand. 40 trillion kilometers is not a travel distance for us. It is a mathematical expression of our physical inaccessibility. It is the universe's way of telling us that we can never be its physical masters. Our bodies were not designed for these distances. Our machines cannot withstand these timescales. Physically, we are trapped in this universe. But here is the beautiful truth, the but turn that emerges right here. But what matters is not how far our bodies can go, but how far our minds can reach. We may be physically chained to Earth, but a 1.5 kilogram brain from inside this skull can look back to the beginning of the universe. It can photograph the shadow of black holes, and it can prove the existence of a planet 40 trillion kilometers away without moving from our spot. Our significance is not in the space we occupy, but in the space we understand. Perhaps what the universe is telling us is not stay here, but understand. You are a part of this paradox. When you look at the sky at night, think about how small you feel. But, at the same time, it is you who knows why those stars you see are shining, how far away they are, and what elements they are made of. Your mind is the most complex tool the universe has created to understand itself. You may be physically small, but your consciousness is as vast as the universe. And this brings us to a second paradox, a paradox of time. On one hand, There is a cosmic time that seems almost infinite. The universe has existed for about 13.8 billion years. Red dwarf stars like Proxima Centauri will continue to shine for trillions of more years. On the other hand, there is our brief, instantaneous existence. The human lifespan is a century at best. Recorded human history is about 7,000 years. This is only 1/10 of the journey to the nearest star with our fastest theoretical ship. How could this be possible? How can such temporary beings dream such permanent dreams? The tragic truth of this question is our mortality. We are a blink of an eye. On the cosmic calendar, all of human existence is squeezed into a tiny fraction of a second. We will not see the completion of any of these journeys. Even the grandchildren of our grandchildren may not see the results of the projects we start. We are beings standing on the shore of eternity, with only a few breaths of time. Our ambitions are as great as time itself. But our bodies are as fleeting as a candle flame. This is the greatest tragedy of man. To desire eternity but be trapped in moments. But here is that beautiful truth again. Because that brief moment is enough. What defines us is not how long we exist, but what we fit into that existence. In just 66 years, a single human lifetime. We went from the first flight to landing on the moon. In one generation, we built telescopes that see the farthest corners of the universe. Our brevity does not make us insignificant. It makes our achievements infinitely more valuable. Every discovery, every breakthrough, is a victory won against time itself. Because we are the species that achieves the impossible in the brief moment given to us. You are a part of this moment. Your life may seem short to you. But, in that brief life, you can see the light of stars that lived billions of years before you. On. You can read the thoughts of philosophers who lived thousands of years ago. And perhaps, a discovery made during your lifetime could change the way humanity understands the universe forever. Your moment is not just yours. It is part of humanity's struggle with eternity. And that is what makes it precious. So, when we understand how limited we are in both space and time, we face the third and perhaps most poignant paradox. The paradox of cosmic loneliness and fundamental connection. On one hand, there is the reality of absolute isolation. We are on a single planet, drifting in the vast, cold, and silent void of space. Our nearest neighbour is at an incomprehensible distance. If a disaster happens, we cannot call for help. No one will come. Our existence on this pale blue dot is incredibly fragile. As this silence, this emptiness, is a fundamental truth of our existence. We are, in a cosmic sense, all alone. The tragic weight of this thought crushes a person's shoulders. That the universe is so big and we are so alone holds an unbearable sadness. But here is the beautiful truth, the most poetic revelation science has offered us. Because the same science also tells us that this loneliness is an illusion. Every single atom in your body, the iron in your blood, the calcium in your bones, the carbon in your teeth was forged in the heart of a star billions of years ago. That star lived, it shone, and it died. It exploded, scattering the elements it created across the cosmos. Those elements drifted through space, they came together, and eventually they formed this planet, this life, and you. We are not separate from the universe. We are the universe itself. We are a manifestation of stardust that thinks, feels, and wonders. Our physical isolation is a game of scale. But our chemical connection is the most fundamental truth of existence. You're the living proof of this connection. When you feel lonely, put your hand on your heart. That beating heart is pumping your blood thanks to iron atoms forged in the fire of a supernova billions of years ago. When you breathe, you exhale carbon atoms that are also the legacy of another star. You're a love letter written to you by the universe. You are the waking dream of the stars. You are not alone. You are home, scale, time, and connection. These three paradoxes are the lessons that the journey to Proxima Centauri teaches us. They show us the brutality of our physical limits, but also the limitlessness of our consciousness. They remind us how short our lives are, but how much meaning we can fit into those brief moments. And they whisper to us that no matter how alone we may seem, we are in fact deeply connected to the fabric of the universe. But there is one more layer to be discovered on this philosophical journey. This is not just about our relationship with the universe. This is about our relationship with each other, because the effort to reach the nearest star is not just a test of technology, it is also a test of humanity. And another paradox that this test reveals is related to the nature of our ambition. And another paradox revealed by this test is related to the nature of our ambition. This brings us to a fourth paradox, the paradox of technological hubris and fundamental fragility. On one hand, there is the incredible technological audacity of humanity. We design 100 gigawatt laser arrays. We dream of gram-scale probes reaching 20% of the speed of light. We plan to build a city in orbit and push it with a fusion engine. We calculate the physics of antimatter propulsion. This is the desire to reach for the power of the gods, like Prometheus stealing fire. Our ambition is, literally, not of this world. It belongs to other worlds. On the other hand, there is the painfully fragile foundation on which these grand dreams rest. A leaking seal, a worn-out bearing, a single radiation hit on a circuit board, or all of these can destroy a trillion-dollar starship, decades of effort, and the hopes of humanity in an instant. How could this be possible? How can such grand dreams be so vulnerable to such small mistakes? The tragic truth of this question is the price of complexity. The more complex you make a system, the more failure points you create. A starship is the most complex machine humanity has ever designed. So, it is also the most fragile. Every backup system, every safety protocol, just adds another potential point of failure. While our technology gives us power, it also leaves us more vulnerable. Because even our most powerful engines are subject to the simplest physical laws, the corrosive effects of time and entropy. But here is the beautiful truth, that this fragility itself is a teacher. These failures teach us humility. They remind us that the universe cannot be controlled, but perhaps it can be understood. They show us how precious every success is, because it is always won on the brink of failure. This fragility makes us better engineers, more careful planners, and wiser explorers. Because our greatest strength lies not in our invincibility, but in our ability to fail and try again. You are a part of this paradox. You may set great goals in your life. But you know that even the grandest plans can be derailed by an unexpected event, a small mistake, or simple bad luck. But this does not stop you from trying, because you know that the real tragedy is not failing, but never trying at all. Your ambition and your fragility are the essence of what it means to be human. So, Professor, all these paradoxes bring us to a fifth and final thought, the paradox of knowledge and mystery. On one hand, there is the vast body of knowledge that humanity has accumulated. We know the age of the universe, we know the chemical composition of stars, we can prove the existence of a planet 40 trillion kilometers away. We have equations that describe the workings of the universe, from quarks to galaxy clusters. Our knowledge is at a level our ancestors could not even imagine. On the other hand, there is an infinite ocean of mystery that emerges with every new answer. What is dark matter? What is dark energy? What was before the Big Bang? How did life begin? And are we alone in the universe? Every time we open a door, we see thousands of new doors appearing before us. How could this be possible? Lawson, how is it that the more we learn, the less we feel we know? The tragic truth of this question is that knowledge is an island, and mystery is an ocean. No matter how much we expand our island, our shoreline with the ocean also gets longer. The horizon of knowledge is the horizon of ignorance. Every new discovery shows us not only what we know, but also what we do not know. This may be frustrating for some. But here is the beautiful truth, that this infinite mystery is the engine of science. If we knew everything, there would be nothing left to wonder about, nothing to discover, nothing to dream about. Mystery is the force that pushes us forward. It is a question that the universe constantly asks us, and this question is more important than the answer. Because this question is what makes us who we are. The species that wonders, seeks, and is never satisfied. You are a part of this infinite quest. When you learn something, you realize that this knowledge leads you to new questions. Your curiosity is your personal science engine, and as long as that engine is running, you will never stop learning. The things you don't know should not scare you. They should excite you, because They are new worlds waiting to be discovered. After learning all this information, after grasping all these distances, these timescales, and these paradoxes, ask yourself this question: what do you feel? On one hand, is there a deep sense of insignificance in the face of the overwhelming vastness of the universe? A feeling of nothingness? On the other hand, is there a sense of awe and wonder at our ability to understand this massive cosmos? A feeling of witnessing a miracle? The answer is that both are true. Because this is the fundamental tension of being human, to be both insignificant and infinitely precious at the same time, to be a physical nothing, but a conscious everything. These two feelings are not a contradiction. They are two sides of the same coin, and embracing this tension is the first step to understanding our place in the universe. Our insignificance teaches us humility. Our value gives us responsibility. Because we are a way for the universe to know and understand itself, and that is the greatest privilege we can have. Scale, time, connection, ambition, and knowledge. These 5 paradoxes show us that the journey to the nearest star is not just an engineering problem, but also a deep philosophical quest, where this quest teaches us fundamental truths not only about the universe, but also about ourselves. We now know that our strength lies not in our size, but in our understanding. Our value lies not in the length of our lives, but in the meaning we pack into them. And our loneliness is the source of our deepest connection. But there is one more question to be answered on this philosophical journey. So far, we have looked out from our home, this planet, to the stars. But what if we do the opposite? What if, from that 40 trillion kilometer distance at Proxima Centauri, we turn back and look at our own pale blue dot? What does Earth look like from that distance? And what does that perspective teach us about our relationship with ourselves and with this planet? Because sometimes the best way to understand who you are is to go far away from home and look back. And that look is perhaps the most important discovery of this entire journey. Because that look shows us not only the universe, but also home anew. And that look shows us not only the universe, but also home anew. So, now, we are descending into the final layer of this philosophical journey. So far, we have asked the big questions about our place in the universe. We have reflected on our scale, our time, and our connection. But now, after receiving this knowledge, it is time to face the most internal and most difficult question. What do we do with this knowledge? How does this knowledge shape our daily lives, our decisions, and our relationships with each other? Because the lessons the nearest star teaches us should not just remain in astronomy books, they should guide the way we live. And this guidance confronts us with new and more personal paradoxes. The first of these paradoxes is the waiting dilemma. On one hand, there is the waiting calculation formalized by Andrew Kennedy in 2006. This addresses a paradox that haunts every interstellar mission. If you launch a mission today with the best available technology, a faster mission launched decades later with more advanced technology will overtake you and arrive first. This means the rational strategy is always to wait for a better propulsion system before launching. On the other hand, there is the existential danger of inaction. If you always wait for better technology, you will never launch. How could this be possible? How can both acting and waiting be both right and wrong at the same time? The tragic truth of this question lies in the nature of progress. Technology always improves. Tomorrow's engine will always be better than today's. It's like standing on the shore of the ocean forever, always waiting for a better boat. But there is a cost to waiting. This cost is not just lost time, it is lost opportunity. An asteroid impact, a climate catastrophe, or a global pandemic may show us that we do not have time to wait. But here is the beautiful truth, that this dilemma itself offers a solution. Because the waiting calculation does not advise despair. It offers us a strategic calculation on when to act. It tells us to find the optimal launch date. And this date minimizes the total travel time by taking our rate of technological development into account. This teaches us that we should not jump blindly, but also not be paralyzed forever. It shows us that we need to strike a balance between research and development and taking action. You also face this waiting dilemma in your life. When you have to make a big decision, You're torn between waiting for more information and acting on the information you have. If you act too soon, you may regret it. But if you wait too long, you may miss the opportunity. This dilemma shows that our problem of reaching the stars is actually a universal reflection of the human decision-making process. And the right answer is often neither to wait nor to jump. The right answer is to know when to wait and when to jump. And this brings us to a second and more unsettling paradox. The paradox of human missions versus robotic missions. On one hand, we have the desire to send humans to the stars. This is one of the deepest romantic and existential impulses of our species. A human walking on another world, a man or woman standing under the light of another star, has a more powerful symbolic meaning than the data sent by thousands of robotic probes. This is the proof that we went there, that humanity has found a new home. On the other hand, there is the unimaginable engineering, biological and ethical burden of keeping a human alive. A 1-gram probe doesn't eat, it doesn't breathe, it doesn't get lonely, and it doesn't get cancer. But people do, and keeping a person alive across 40 trillion kilometers may be much harder than getting them there. How could this be possible? How can our greatest dream also be our greatest obstacle? The tragic truth of this question is the fragility of our biology. We are machines perfectly tuned for the biosphere of this planet. But not for the vacuum, radiation, and cold of interstellar space. A human mission is not just a propulsion problem, it is a problem of radiation shielding, closed-loop life support, long-term mechanical reliability, food production, medical care, psychological resilience, and social stability. And each of these problems on its own can make the mission impossible. But here is the beautiful truth that this challenge makes us a better species. Because the problem of sending humans to the stars forces us to solve our most urgent problems on Earth. Closed-loop life support systems can help us solve the problem of resource scarcity on Earth. Food production in space can make agriculture on Earth more efficient, and radiation shielding research can lead to breakthroughs in cancer treatments. The effort to reach the stars is not just about the stars, it is about making Earth a better place. The challenges of sending humans are also the source of humanity's greatest innovations. You are a part of this paradox. In your life, you realize that sometimes the most challenging goals are the ones that develop you the most, because these goals force you to step out of your comfort zone, learn new skills, and become more resilient. The dream of sending humans to the stars is humanity's most challenging goal, and that is why it is also the most rewarding. So, when we find a balance between acting and waiting, and understand the value of both human and robotic missions, we face a third and final paradox, the illusion of proximity and the reality of distance. On one hand, there is the psychological proximity created by phrases like the nearest star and a neighboring world. The discovery of Proxima Centauri b made headlines worldwide because it made us feel that we have a target, an attainable destination. These words make 4.24 light-years seem like a manageable, even modest, distance. On the other hand, there is the brutal physical reality of this distance, 40 trillion kilometers, a distance that Voyager 1 would cover in 73,000 years, a distance that Parker Solar Probe would cover in 6,700 years. How could this be possible? And how can the same reality be both so hopeful and so discouraging? The tragic truth of this question is the inadequacy of language and human intuition in dealing with cosmic scales. Our brain has evolved to understand earthly distances like crossing oceans or climbing mountains, but not to understand light years. The word nearest tells us a rank, but it does not give a guarantee of accessibility. It's like standing on top of Mount Everest and saying that the next nearest peak is on the moon. It is technically correct, but thus practically meaningless. But here is the beautiful truth that this illusion, this misunderstood proximity, is the greatest fuel of human ambition. If we had fully grasped the true scale of the distance from the very beginning, perhaps we would have never dared to dream. That false hope created by the word nearest is the spark that pushes us to explore, to invent, and to push the boundaries. It is humanity's way of looking in the face of impossibility and saying, "I will try anyway." The illusion can disappoint us. But it can also lead us to our greatest achievements. You also know the power of this illusion. Have you ever embarked on a goal in your life that seemed easy at first, but then turned out to be incredibly difficult? Perhaps that initial naivety, that misunderstanding, was what got you started, and along the way, you learned lessons that were more valuable than the goal itself. The illusion of proximity can be a trap, but it is also an invitation, a call that invites us to see what reality is with our own eyes, waiting and acting, human and machine, illusion and reality. These paradoxes show that the journey to the nearest star is not just a problem of physics or engineering, but also a deep human drama. It is a story of our hopes and fears, our ambitions and our limits. And as we approach the final act of this story, it is time to put everything we have learned so far together. We now know that the journey is impossibly difficult. But we also know that the desire to embark on that journey is a part of what makes us who we are. But all these thoughts bring us to one final question, perhaps the most important one. What is the ultimate purpose of this journey? Is it just to survive? Is it just to reach another world? Or is there more? Because maybe going to the stars is not just about finding a new home. Maybe it is about redefining who we are. And this process of redefinition forces us to look not only outward, to the stars, but also inward, to the deepest and most contradictory truths of our own existence. Because the ultimate lesson of the effort to reach the nearest star is perhaps not about reaching a destination, but about who that journey makes us. So, now, we are entering the innermost layer, the final act, of this philosophical journey. So far, we have questioned our place in the universe, our time, and our connection. But now, at the end of this journey, it is time to understand what this knowledge does to us, how it transforms us, and what it leaves behind. Because this final layer contains the most personal paradoxes, and the first of these paradoxes is the paradox of success and failure. On one hand, there is the fact that the story of interstellar travel is, to a large extent, a story of failure. Project Orion died due to political obstacles, Project Daedalus remained on paper, and even the most modern, most minimalist attempt, Breakthrough Starshot, stalled after spending only $4.5 million of its initial $100 million commitment, hitting the wall of engineering reality. Every serious attempt was either postponed, cancelled, or failed to move beyond theory. This is a tragic proof that humanity's greatest dream is also one of its greatest defeats. We are a species that dreams of reaching the stars but has not yet been able to launch even a chip from our backyard. On the other hand, there is the fact that these failures themselves are a hidden success. How could this be possible? How can constantly losing be a form of winning? Because these projects may not have reached their goals, but in the process, they created something priceless: knowledge, innovation, and inspiration. Starshot advanced research on laser phase arrays, nanoscale spacecraft, and light sail materials by decades. Orion and Daedalus allowed us to understand the limits and potential of nuclear propulsion. Every failure became a textbook, a stepping stone for the next generation of engineers and scientists. But here is the beautiful truth, that the real success is not even in these technical gains. The real success is in the act of trying itself. It is to show the audacity to pursue the impossible. Because this quest does not only teach us physics, it teaches us what perseverance, creativity, and hope mean. You are a part of this paradox. There have been goals in your life that you could not reach. Maybe you failed an exam, didn't get a job, or couldn't realize a dream. But didn't the things you learned during that process of failure make you who you are today? Didn't that effort make you stronger, wiser, and more resilient? The effort to reach the stars is the process of building humanity's collective character. And in this process, the destination becomes less important than the journey itself. And this brings us to a second and more poignant paradox, the paradox of the destination and the starting point. On one hand, there is that destination that is the focus of all this massive effort, all this sacrifice. Proxima Centauri b, it is the mission, it is the goal, it is the why of everything. Well, it is that faint beacon of hope that unites humanity, that ignites a multi-generational effort. On the other hand, there is the fact that that destination will most likely be a disappointment. As we have seen before, Proxima b is most likely a radiation-scorched, atmosphereless and tidally locked world. This means that with $1 trillion mission, a century of effort, and the lives of thousands of people, we might only reach a dead rock. This could be the greatest anticlimax, the most tragic disappointment in human history. How could this be possible? How can our greatest hope contain the seeds of our greatest disappointment? But here is the beautiful truth, that this potential disappointment teaches us the most important lesson, and that is the value of home. Because when we travel 40 trillion kilometers and find a world hostile to life, we understand how precious, how rare, and how miraculous that pale blue dot we left behind is. As Carl Sagan said, that little dot is everything we know, all our joys and sorrows, all our religions and ideologies, all our kings and peasants have lived there, on that speck of dust suspended in a sunbeam. The effort to go to the stars, perhaps ironically, is not about the stars, it is about Earth. It is about leaving home and truly appreciating home for the first time. You know this feeling too. Sometimes you understand the value of something only when you face the risk of losing it. Sometimes, while chasing a distant dream, you realize how precious what you had in the first place actually was. The journey to Proxima Centauri is humanity's journey home, a journey that shows us how vast and empty the universe is, and how small and precious our home is. So, when we understand the wisdom of failure and the value of home, we face a final paradox, the paradox of silence and voice. On one hand, there is the great silence of the universe. For decades, we have been listening to the sky with our radio telescopes. We are looking for a signal, a whisper, a proof that we are not alone. But all we have found is silence. This is a chilling fact that underlies the Fermi paradox. The universe should have been teeming with life, but we see no trace. This silence stands as the strongest evidence of our cosmic loneliness. It is a tragic note at the core of humanity's existential anxiety. On the other hand, there is the fact that this silence makes our voice infinitely more important. How can a universal silence make our existence more meaningful? Because, if the universe were filled with a divine voice telling us what to do, what meaning would our free will, as our creativity, and our moral choices have? If the universe had a purpose, how valuable would our struggle to create our own purpose be? But here is the beautiful truth, that this silence is the greatest gift the universe has given us. This silence is a blank canvas, and the task of painting that canvas has been given to us. Because the universe is silent, our music, our art, our science, and our love become the only voice in the universe. We are the species that brings meaning to a silent cosmos. We are the beings who create purpose in a purposeless universe. This silence is not a curse, it is a responsibility. It is the universe's way of telling us, you write the story. You are a part of this creative act. In your life, there may not be a clear roadmap telling you what to do. Sometimes, you have to create your own path, your own purpose, your own meaning. And in those moments, when you find your own voice in the midst of silence, you exist in your most authentic and most powerful form. The silence of the universe is an invitation for you to sing. The wisdom of failure, the value of home, and the voice of silence. These final thoughts complete the philosophical map of our journey to the nearest star. We now know that this journey takes us not only to another world, but also to a deeper understanding of ourselves, and it teaches us that our physical limits do not define the greatness of our consciousness. It reminds us that the brevity of our lives does not diminish our power to give them meaning. And it shows us that our cosmic loneliness increases our responsibility to create our own meaning. We are approaching the end of our journey. We started with the brutal equations of physics. We crossed the impossible challenges of engineering, and we navigated the deepest philosophical paradoxes of existence. Now it is time to put the pieces together. Now, it is time to look at this terrible and beautiful truth one last time and, in the light of all this knowledge, return to the simple question we asked at the very beginning. Why is even the nearest star so far away? Or because? We now understand that the answer to this question lies not only in the trillions of kilometers, but also in what that distance teaches us about ourselves. And this final answer, in this video, we saw how vast and old the universe is. But there is something I didn't tell you. All of this 13.8 billion year history might only be half the story. What if there was another universe before everything? What if the Big Bang was not a beginning, but a beginning that came after an end? In our next journey, we will look before the Big Bang. Are you ready?